Welcome. Let's explore a triangle of numbers. I'm going to do this in an unusual way, but I'm going to go against my principles and basically tell you this whole process rather than spend some time with students. We'd go through this over an hour or something. Here goes. Here's a famous puzzle that's going to lead to something interesting. Here's a grid of squares. Here's the start box. Here's the end box. And I'd like to walk from start to end, but I'm only going to allow myself to take steps to the right, one square over to the right, or steps down, one square down, and that's it. I'm not allowed to move diagonally, I'm not allowed to move to the left, I'm not allowed to move up. How many ways can I go from start to end? Well, obviously there's a good number of ways. I can go right, 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 down, 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 down. It's a very easy way. Or we can do some mixture of things. Right, right, down, down, right, down, right, 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 down, right. So I'd like to know the total number of possibilities. And that's going to be a bit of work. What I would do with kids is we'll play with this and we'll get frustrated. And we might try simpler examples first. For example, how many ways can I walk to this square? Well, there's only one way to go from start to there. Just take a step to the right. So the possible number of routes from start to that square is 1. In fact, if you think about it, the number of ways to get from start to any square on the top row is 1. I can only move to the right. There's only one option. Ditto for the rows going, cells going down a column from the start. There's only one way to get down to, say, this bottom cell down here. I only take 4 down steps. Now let's get a little more interesting. What about this cell here? How many ways can I walk to this cell? Well, I can actually count them. I can go right down or I can go down right. There's 2 ways to get to here. What about this one over here? Now things are a little more complicated. Let me start writing that. I could have right, right, down, right, right, down, or I could have right, down, right, right, down, right, or I could have down, right, right, down, right, right. Looks like there's 3 ways. In fact, that was a nice way to list it. If I looked at this next cell, I could go right, 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 or down, and then I can play the same game and see there's actually 4 positions that D could be amongst the 3 rights. So actually there's 4 ways to get to here. And if I look at this cell here, that's actually down, down, and a right. 2 downs and a right, so it's really the same problem as this one, but just the letters reversed, 4. And I bet we can have a guess what this next elements of the row is going to be and the next elements of this column are going to be. But rather than go there for the moment, let's look at this cell. How many ways can I get to that cell? Well, what I'm doing now, I can start listing possibilities. I could go right, right, down, down, right, right, down, down, or I could go right, down, right, down, right, down, right, down, and so on. That's fine. I can list those, and I'll talk about that approach in a moment. But there actually is another way to think our way through it. In order to get to this green dot, I've got 2 options. Either get myself to the cell above it, and there's 3 ways here, and then take one of those 3 paths and go down to the green dot. Or get myself to this cell on the left. There are 3 ways to get there, and I can take one of those 3 paths and then take a single step to the right. So that means to get to the green dot, either go to the cell above it, 3 ways to get there and take a step down, or go to the cell to the left, 3 ways to get there, take a step right. That's a total of 3 plus 3, 6 ways to get to that particular cell. In fact, that argument is beautiful because it allows me to quickly start filling in the rest of the cells of the diagram. For example, to get to this cell here, either get yourself to the cell just above it, 4 ways to get there and take one of the 4 paths down, or get yourself to the cell on the left, 6 ways, and there's 6 ways to then take a step right. So there's a total of 4 plus 6, 10 ways to get to this cell. Well, that means I can fill in this whole diagram now pretty quickly. 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 1 is 8. Yes, that indeed was the counting numbers. 10 plus 5 is 15, 15 plus 6 is 21, 28, 36. In fact, I can get myself down here pretty quickly. I'm going to do it. 4 plus 6 is 10, 10 plus 10 is 20, 35, 56. Oh, that's getting hard. 84, 84 and 6 is 90, 120. Last one to go. 1 plus 4 is 5, 15, 35, 70, whoops, 126, 210. There must have been then, looks like 330 ways to go from the beginning cell to the right cell, to this lower right corner, using only rights and downs. Okay, I'm actually going to write a formula for these numbers now, and we've actually done this in another video, so I'm going to ask us to go to the video on y is 0 factorial 1. And if you've watched that video, you will know what we're really doing here. To get to this e, I need to take 1, 2, 3, 4, 5, 6, 7 right steps, right, 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 followed by 1, 2, 3, 4 down steps, and that's, whoops, down, and that's one possible route from S to E. But of course, any route would be some combination of R's and D's, and it always involves 7 R's, and it always involves 4 D's. So going from start to end is really the equivalent to asking the question, how many ways can I arrange a word, if you like, of 7 R's and 4 D's? Well, in the y is 0 factorial equal to 1 video, we learnt that the number of ways to arrange this word would be the number of letters there are, 11, made factorial, over the number of r's there are, 7 factorial, divided by the number of d's there are, 4 factorial. And I bet if you work this out, it is indeed 330. So I actually have now a formula for the entries of this grid. For example, what is this 15 really? Well, it's coming from 1, 2, 3, 4 r's and 2 d's. There's a total of 6 letters, 4 of which are r's and 2 of them are d's. So that's 15 is really 6 factorial over 4 factorial over 2 factorial. All right, what has this got to do with Pascal's triangle? Well, it's sitting in us, at us right now, we can see it. Look at these numbers. Turn the grid diagonally sideways and read things diagonally. So instead of looking at rows and columns, I'm going to look at the diagonals this way. And I see the first diagonal is 1, 1. I've got an S at the top. Then I see 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This one's going to be a 1, so it's going to be 1, 5, 10, 10, 5, 1, 10, 10, 5, 1, and so on. This triangle is very famous, called Pascal's triangle. It has many different names in different nations. It's been around for literally thousands of years. Just we in the West tend to give a name Pascal because he's the first of the Western scholars to have done something significant with this triangle in probability theory. But I do have a question. That S at the top, most people write a 1 at the top. Is that valid? Well, let's see. Let me go back to my formula idea. Here's a 1 here. That represents how many r's? 1, 2, 3, 4, 5 r's. And how many downs? 0 downs. So in the y is 0 factorial equal to 1 video, we would know the number of ways to get here to arrange 5 r's and no downs would be the total number of letters is 5 divided by the number of r's factorial times the number of d's factorial. Well, that's equal to 1, so it's really 5 factorial over 5 factorial is indeed 1. So if I follow this formula here for the s, that's 0 r's and 0 d's. So according to the formula, that would be the total number of letters, 0 factorial, divided by the number of r's made factorial, divided by the number of d's made factorial. It's 1. So let's actually make this a 1 at the top of the grid. Now, I've turned things sideways here. Let me go back to this. Oh, I don't have the 15. Let me write the 15, sorry. That's the next row. 1, 6, 15, 15, 20. What am I saying? 15, 6, 1. Let's look at this 15, which I believe is the 15 over here. We said it was, did I write it down still? No, okay, well let's figure it out. It's 1, 2, 3, 4, 1, 2, 3, 4 r's and 6 d's. What am I saying? 2 d's. Total of 6 letters, 4 r's and 2 d's. Now how do I translate that to this rotated picture? Well, a little bit of work, and you have to think your way through this, is to say that, well, this 6 really corresponds to which row I'm on. But, watch out. This row corresponds to having no letters at all. Let's call it the 0th row. This row corresponds to having 1 letter. Let's call it the 1th row. Here it is. It was either 1R or 1D. This row corresponds to having 2 letters. Let's call this the 2th row. They correspond to either having 2 Ds, 2 Rs, or 1 of each kind, and so on. So look at this. Our 15 turns out to be on the 6th row. So the numerator represents which row in Pascal's triangle we're on. Now, this 4 is interesting. It looks like in Pascal's triangle we're counting from beginning with 0. Let me count 4 places in, starting at 0. 0, 1, 2, 3, 4. Bingo. Let's count 2 places in from the right. 0, 1, 2. So actually, if you think it through, this does correspond to the number of r's and d's that need to be 15. It translates this way on the diagonal picture, that the 2 numbers on the denominator represent how many places in from the left, how many places in from the right you need to come by counting starting the counts with 0. So for example, what is this 4 really? Well, according to Pascal's triangle, I seem to be on the 0th, 1th, 2th, 3rd, 4th row. So it's 4 factorial. I am 0, 1 place in from the left. I am 0, 1, 2, 3 places in from the right. And that is indeed the number 4. So there it is. There's a formula for the entries of Pascal's triangle. Finally got there. Thank you.